Good afternoon. Welcome everyone to the Georgia Tech Manufacturing Institute's Lunch and Learn lecture series. My name is Billy D. Brown. I'm a research faculty with the Georgia Tech Manufacturing Institute and Director of Manufacturing Education Programs. GTMI is one of 11 interdisciplinary research institutes at Georgia Tech that uniquely focuses on manufacturing research, development, and deployment. We help tackle the grand challenges of today's manufacturers and assist partners in moving innovation from lab to the marketplace. GTMI has a wide variety of facilities and equipment located on main campus for basic research, as well as 14th Street for more applied research and our advanced manufacturing pilot facility. GTMI's mission includes education and workforce training, collaborative partnerships with industry, academia, and government, as well as thought leadership. GTMI hosts the Lunch and Learn series every semester. And this spring, sessions will be held Monday at noon as live online events. These sessions are excellent opportunities for Georgia Tech faculty, researchers, undergraduate and graduate level students, as well as a global manufacturing community to share advanced manufacturing knowledge. To ensure a smooth presentation experience, all audience members are automatically muted. If you have questions or comments for the speaker, please use the question and answer panel on your screen. I strongly encourage you to please submit your questions to the Q&A panel as soon as you have them so the speaker can address them at the end of the presentation. Today, I'm pleased to introduce Tim Bell, who will discuss industrialization of additive manufacturing through digitalization. Tim Bell is the head of the Center of Competency for Additive Manufacturing within the Siemens Digital Industry USA, and is a seasoned manufacturing veteran and Cincinnati, Ohio native. He has spent more than 30 years in manufacturing and was trained as a journeyman toolmaker in the 1980s. He spent the next 20 years as a machinist, a programmer, designer, and entrepreneur of small contract manufacturing companies. The last 15 plus years have been focused on additive manufacturing of components and assemblies supporting the aerospace, defense, and medical industries. He has successfully launched 4 U.S. companies, 2 of which were foreign-owned joint ventures, taking them from ground zero to profitability and becoming leaders in their respective fields. Tim is often considered a pragmatic go-getter who thrives in tackling new challenges with creativity and experience. In today's session, Tim will focus on today's ever-changing manufacturing environment and the meaning of buzzwords like digitalization, Industry 4.0, and IoT. Today, a lot of companies say they are digital, but what does that really mean? How do you digitalize your manufacturing process? And most importantly, what value does it bring to your operations? Siemens is the global leader in digitalization and the only company who can provide true end-to-end solutions to additive manufacturing market, using their software and hardware tools such as MindSphere, a cloud-based IoT interface. Right now, Tim will introduce us to some amazing ways Siemens can help companies digitalize their additive manufacturing operations. Tim, you may begin your presentation.
Thanks, Billy D, and thanks for having me here today. I really appreciate the opportunity to speak with you guys and share a little bit about what we're doing. So industrialization of additive through digitalization. Siemens is a very interesting company. More than 170 years ago, it was founded with an idea that a company should not only focus on maximizing profits, but it should also serve technologies and employment practices. Siemens looks at this today no differently than they did 170 years ago. We focused on streamlining who we are to achieve these. Today, we're a leading technology company. We provide industry-specific support to our customers. We're about 300,000 employees, around 60 billion euros in revenue. Basically, you can see we're pretty large. As of October 1st, we actually spun off our Siemens Energy in Gamesa, which was your gas turbine engines, generators, and wind turbines, to focus more on technologies. Within Siemens, our businesses are broke up between digital industries, smart infrastructure, mobility, Advanced Consulting, and some portfolio companies, and Siemens Healthineers. I come to you today from the digital industry side of the business. Within the digital industry side of the business, we focus on industrial software, factory automation, motion control, and process automation. We also have a huge customer services team to do support and engineering services. Why Siemens Digital Industries? I won't go through all this, and we'll make the slides available afterwards. But basically today we ship about 10,000 PLCs daily. As the number one leader in PLCs, number one industrial software, factory automation, and motion control. And I think what's most interesting on this slide is the global domain expertise. We have over 12,000 industrial software engineers and over 20,000 automation engineers. Siemens is very dedicated in supporting our customers in this journey. Additive manufacturing is a core technology for Siemens as a supplier, end-to-end software, automation, digitalization solutions. What a lot of people don't know is we have more than 10 years experience in using additive manufacturing, as well as being a service provider with our facility of Material Solutions in the UK. Today we have over 150 industrial AM machines. I can tell you that about 75 of these metal powder bed fusion machines run 24/7 running production components. We've got way more than 200 desktop machines floating around the world. I think we're getting closer to about 450 total machines globally now. When you talk about additive manufacturing, it's relevant in a wide range of industries, from machines to power to aerospace, automotive. I mean, it just runs the gamut. What a lot of people don't realize is there's even additive manufacturing components in some consumer electronics like the phone in your pocket. Yes, the answer is additive can do high volume production. As it being a core technology for Siemens, we've taken things within our own and we've built tools around our own use of additive, and now we're bringing to the customers out in the world. One of those examples is this conventionally manufactured burner. So this is a burner tip for a large gas turbine engine. It's traditionally made from 13 machine parts joined by 18 welds with thermal barrier coatings. And a big point there on that bullet point is 26 weeks lead time. Whereas optimized, designed as a single piece to be 3D printed, it's a 3-week lead time. This is massive in the repair and service industry of gas turbine engines. To be quite frank, there's not a lot of brand new engines being sold in the world as we're trying to push away from fossil fuels to create energy. But there's so many engines out there that need service, and we're looking for better ways to make these engines more efficient, better performance, and get service parts out faster. So we leveraged additive here. Another place that Siemens has leveraged additive is within our mobility, where we make trains, our biggest market within mobility. We have 8 locations now, and over 800 parts are available for on-demand printing, meaning that a service technician can go into the train, he can have an iPad, pull up the components that's broken, even by just taking a picture of the component, pull up that component, and then the system will tell the customer, hey, you can print that on demand, and here's a pickup location. So today we've printed over 8,000 parts for our mobility group with over 100 satisfied customers. This is where I talk about how we drink our own Kool-Aid or eat our own dog food. We use this for ourselves and for our customers, and additive has such a broad range of applications for us. Another area is our health and ears group. These folks are responsible for building CAT scan systems, X-ray systems, sonogram systems, a lot of these very complex medical machinery. And that team has utilized additive for rapid iteration, rapid tooling, things like that. So it's amazing to see, as you see this top picture on the left, you see the home style, MakerBot or Ultimaker there. These machines are used every day in product design within Siemens. So what are the drivers for industries? They're all different. Every industry has a different reason to look at additive manufacturing. It'll be product transformation or manufacturing transformation. Reimagine your products, scan to product, reduce weight. You can rethink your business, individualization, personalization. There's a new buzzword out, mass customization. We have tools to allow our customers to do that every day. But I think reinventing manufacturing is a really solid place to look at for eliminating molds and casting and tooling, simplifying assembly processes, Additive is used for so many of these things. Where does additive make sense? Well, it's typically in high complexity components that have a high value. But what we're seeing over time is the additive technology is being enabled by digitalization to move towards mass production. If you follow additive manufacturing news, you saw recently where X1, one of our great customers, announced their development with Ford, where they productionized binder jet with aluminum. This is a huge step towards additive going to mainstream mass production. The market's growing strongly. The CAGR for the additive market is about 25% annually. This is huge. This is massive. This tells us that it's on the way to becoming mainstream. So how do you leverage digitalization for additive manufacturing? Well, let's look at digitalization. It's a pretty basic definition in the process of converting something to a digital form. Well, that's kind of misleading. You can't just convert it and say, oh, I've digitalized my manufacturing process. What Siemens has done is given you the ability to connect the virtual and the real world. This is digitalization. We're so used to designing components in CAD systems, and then we move that over to software, do simulation, and then we send it to the shop floor, and that machine's disconnected, and we try to put all these pieces together to make a solid manufacturing process. Unfortunately, today we don't have that in the additive world, but Siemens is bringing that to the forefront today. The barriers to additive manufacturing are the same as other ones. It's what I just said: design, simulation, print preparation, the process, heat treat, finishing, inspection. All of these are a disconnected process chain. So many different platforms. What Siemens has done is we've tried very, very hard to create a digital enterprise, allowing you to, I don't want to make this a software pitch, but basically go into a software platform and stay in it for the entire path. So from cradle to grave, and then more importantly, the digital twin performance. So feed that performance data back into the virtual product. And I'm going to show an example of that here. So let's start out with a digital twin of the product here. So I took an example here. This is an automotive base frame component. So you see there's a node or a module there where some frame tubing is connected, and the nodule or the module there is 3D printed. So digital twin of the product. We start out with designing the product. So we're going to design the product. We're going to use generative design, topology optimization, and then we're going to take that design and bring it into convergent modeling, where we can move it around and do some more things and make it more fluid. Then we can even validate that the design physically, its physical behavior in the same platform, and then most importantly, moving that same model within never leaving the same screen, and checking the printability. This is the key to additive manufacturing, because the processes are much more variable than traditional manufacturing. So there's a lot of things that go on. You've got a lot of stresses. You've got a lot of influencing of the build based on the environment or the health of the machine. So being able to check printability, optimize the design, validate the physics of the actual component in its atmosphere, being able to do all this in one single digital twin starts to change the way we manufacture. Now let's look at the digital twin of the production. Here, we can prepare the parts for printing. We can predict how they're going to print. We can also start planning post-processing, whether it be port removal, inspection, whatever it might be. So again, you've got the digital twin of the product. So you've designed it, you've simulated it in its environment, you've checked its printability. Now you're going to come over to the digital twin of the process. You're going to prepare the parts for printing. You're going to add support structures, you're going to orient the components on the build plate. You're going to predict and compensate for the thermal distortion. If you've ever done any 3D printing, and you know with metals specifically, you're going to get a lot of distortion. Planning for the removal of support structures is key, because if you ever had to remove any, it's a pain in the butt. And then even being able to do the same thing, never leaving the software, and do your inspection process. This has never been done before with any other technology other than maybe mold making. Now if we go on to the real production, connecting the equipment. This is the true point of digitalization. Connecting the equipment to this digital twin of the product and the process. So now, equipment that utilizes Siemens PLCs, IPCs, CNC controls all have the ability to be connected. When I say connected, they can be connected to an MES system. They can be connected to a Team Center, a PLM system. They can be connected to an ERP or a mass scheduler, and they can all be together as one. You can see what's on machines, what's running, how much time is left, and even go so far as to start collecting OEE data. Now we're getting into the real stuff. Now we're talking about the real product. Now imagine we virtually designed the product, we virtually produced it, now we've actually produced it, now we have results, and we can take those results, whether they be physical from the component or whether they be digital from the asset, the machine, the feedback from the machine, and we can feed it back to the beginning again and have a continual improvement process where our product is always getting better because we're measuring the outputs, comparing them what they should have been, and making changes accordingly. Hope everybody kept up with that. Now let's talk about digitalization of an additive manufacturing machine. So we talked about the product, the part, the process, the real world. Now you can take that same philosophy of a digital twin of a product, and you can design a machine. And say you design the machine, it doesn't have to be NX, but it shows NX here. You've designed the machine, you have all the kinematics ready. Now the problem always happens with building a machine is you spend all this time designing, you have to wait for all the hardware to get in, start assembling all the hardware, checking for all the fit and function and movability and axis squareness and level and plane. And on the same time, the electrical engineer or the automation engineer is looking at you like, hurry up, I need to get my stuff in here so I can test my code. Well, what we've done is we've taken that same approach. Take the kinematics, add multi-physics to them, simulate the actual machine with gravity, with weight, with force. Now also add a simulation of the PLC. Here we talk about our Siemens NX MCD, that's a mechatronics concept designer, and SIMIT and PLC Sim Advanced. So what you see here is X1's latest printer that they released about a year or so ago, the S-Max Pro. They literally did all of their development virtually. The physical of the machine, wrote all the code for the PLC, did the testing and development of the PLC code on the actual multi-physics kinematics models, and were able to troubleshoot everything months before the machine actually hit the floor. They've told us that in the past, a new model would take them 3 months of commissioning on the floor for the first system. They did this in 3 days once the machine. This is groundbreaking. While it's groundbreaking for them, for their development of their systems, I think what's more groundbreaking is COVID happened, and they needed a way to train their customers without being on site. And they were able to use these tools of their virtual commissioning, the digital twin of that machine, to train their customers, train the service personnel, and literally walk everyone through. And that when the machine was delivered, that first machine, their operators were ready to go when it hit the floor. It's an amazing story, and we're so proud to be part of this. And the real production. This particular machine is equipped with Siemens hardware, our S7-1500 controller, which is probably the most powerful PLC in the world, our IPCs, standard industrial communications with Profinet and OPC UA, our standard drive systems, an S120 compact drive, our servo motors, industrial controls, distributed I/O, and on top of that, this was all engineered with what's called TIA Portal. TIA Portal simplifies the programming of a PLC process by allowing you to go into a portal that has almost every type of machine motion pre-configured in a menu. Because even though this is a 3D printer, it's got an x-axis that moves. Well, that same code has been written for thousands and thousands of other machines. You could pull those down, and you don't have to write all the code to the PLCs. Use TIA Portal to your advantage. You can use WinCC HMI to develop the HMI the way you want, and then you can even have remote connect. What X1 did was they went to the next level, and they took our MindSphere, it's our Industrial Internet of Things operating system, and they built applications for their customers. They call it 3D Live. Their customer actually has an iPad or even their iWatch or tablet or desktop computer where they can see live what the machine's doing, whether it be print job information, layer state and progress, powder and binder fill levels, and transparency on the operations. So what have they done is they've created live OEE, operational equipment effectiveness. More importantly, they also have the ability to measure the quality coming out of the machine based off of the feedback from the motors and the drives and the controller and the switches and the sensors. So not only are they using this digital twin and this digital thread to produce a component, but also manage the quality, manage the efficiency, and most importantly, manage their productivity, which is performance and revenue, because that's what customers buy manufacturing equipment for, is to generate revenue. So here's a great example of how they seamlessly integrated the software and automation solutions into this digital thread. Again, the digital twin of the product, the digital twin of the production, the real production, and the real product. There's a good screenshot on the right there on that laptop showing how the dashboard of running the machine. And you can have multiple machines. Interestingly enough, you can run this on AWS cloud, or you can have a on-premise cloud to run these, because we have a lot of defense customers. Say in the additive industry, there's a lot of defense customers, and they demand an on-site cloud system. If we look at the additive manufacturing landscape today, there's probably about 300 industrial machine builders globally. And today we have more than 80 of these machines leveraging the power of Siemens controls. Whether that be our somatic product line on the left bottom there, which is our PLCs and IPCs. As you can see, we've got 15 powder bed fusion manufacturers, 2 material extrusions, and 8 jetting companies using somatic PLCs. On the right side is a Cinemeric. If you've ever been in a machine shop and you've seen any 5-axis machine systems, you've seen a Cinemeric control. This is the world's leading control for multi-axis systems. 28 DED machine OEMs use this control, 16 material extrusion, 1 powder bed fusion, and 1 jetting. There's a reason behind this, and there's a reason this is going to get even larger. Interestingly enough, we have a product called Cinemeric Run My Robot Direct, where you can actually program a robot using G-code that comes from a standard CAM platform, or writing it longhand even. This is changing the way people look at robots. And we also have the ability to make robots much more accurate than they traditionally are. Moving on, I'm going to show you an interesting design from simulation. When I talked about the digital twin of the product and the digital twin of the process, imagine, you've all seen generative designs and topology optimization. Typically, this is done by some physical constraints of a component in an assembly. And the topology optimization is usually lightweighting and trying to take advantage of additive. But part of the problem with topology optimization is people have a hard time, if it's a structural component, accepting that futuristic looking design. And how do I use that? And how do I sign off on that? Well, what I'm going to show here is how our partner HP literally took a component inside of their 3D printer, used our CFD software, Star CCM Plus, to redesign the geometry for maximum flow without any respect to a manufacturing process. Meaning, typically when you design something like a duct, you're designing it around how it can be made. Rather, in this video I'm going to show you, and I apologize if there's not sound, we have a technical problem this morning, but I'll walk you through it, where we use CFD to generate the design. At the end of the day, this new part reduced the cost by 34%, but increased the flow to 23%. I apologize, you can't hear the sound, but this is how CFD optimized. On the left, you see the standard part. On the right, that's my wonderful boss, Dr. Karsten Hauser, based in Germany. Here you can see a gentleman using NXCAM. He was doing some nesting. Here we're talking about leveraging simulation to generate the design. On an HP printer, for an additive printer, one of the problems is keeping the ink or the jetting nozzles cool. If you don't keep your jetting nozzles cool, you're basically squirting out glue. And if you don't keep them at a specific temperature, the viscosity of the glue is not where you need it to be, and you're going to get zero performance and clogged nozzles and all these things. This came from having a meeting with HP and trying to figure out what kind of part can they demonstrate generative design and topology optimization. And no one ever thought about this duct. It just happened to be sitting on a table. They picked it up. So this is traditional duct. It's printed out of on one of their systems. Here you can see it in the design. And the duct actually cools these printing nozzles. This is the traditional duct and its flow, and you'll see a better video of it here in a second. And the flow is really, really not up. There you can see that this was printed in 3 components even, not 1 component, because the design wasn't able to be printed as one either. So we went through some simulations to say, okay, let's take this duct and let's use CFD, optimize the flow. Traditional duct had a lot of waste in it and a lot of losses here. You can see the turbulence, and you can see there's just a ton of losses in that. Now, here's the new version, and you can see the losses are much less. And what's interesting is this shape. And Ashley talks about here how you had to take this output data, and you can see this. The output data was just voxels. There's just blocks of information to say, and this is the shape. Then he had to turn this into a thin wall. Once he had it into a thin wall, he stopped and looked at it and thought, what in the world? I would never have imagined designing a component that looked like this. You know, typically, you would design all the fillets and radiuses and wall thicknesses and brackets. But in this, you just said, this is the beginning, this is the end, use the flow data. And yes, it looks like a tongue sticking out the end of that. Again, no one would ever design that component. It required designing from data. Interestingly enough, we've added some more functionality to our NX design platform to allow you to do algorithmic designs even. So we're taking this digital thread and digital thought process to the next level and designing smarter components, not just components that fit the bill, if you will. Jump through here a little bit. Since we can't hear anybody talking, there's another good view of this. And if you want to see this video, it is online. You can access it through YouTube, Siemens HP Duct. I can share that as well. There you can see the 2 versions of it. So anyway, that's a great example, and we have many of these examples of printing a design that historically you would never have been able to do. So I've talked about the digital thread and the digital twin of the product and the process equipment. Now what's next? Next is the factory. In our world, working with so many of these additive manufacturing machine OEMs, you know, they come to us with the hard problems. If it was a problem in their wheelhouse, they would solve it themselves. But they came to us and they said, hey, with your virtual twins of the machines, actual kinematics and physics models and the PLCs, can you simulate multiple of these machines in a factory? We said, sure we can. We have a product called, it's Factory Sim, basically. It's Technomatics Plant Simulation. And the reason was a customer went to a large powder bed fusion manufacturer and said, hey, we need to buy 65 of these machines. Can you verify this? And the manufacturer said, yeah, as best you did with some spreadsheets. They came to us and said, what can we do? So we built a model. What you see here is the EOS M300, which is the newest EOS machine, and it's 100% Siemens controlled. And you're going to see some AGVs that are 100% Siemens controlled. What we were able to do was take a specific component, start processing it in the machines, start building the shop floor to determine, based on a number of components per year, how many machines they would need, how many AGVs they would need, how many powder separation systems, how many build boxes they would need, how many post-processing machines would they need, whether it be robots or 5-axis machining centers, and built this factory virtually. And this isn't just pictorial or video simulation. This is actual simulation of the factory, machines actually running. And we start doing the simulation. And as soon as it pushes play here, it says, okay, number of body sets is 113. And then it can visualize it. You can see all the utilization parameters. So this is for the stations, for the printers. You can see utilization for the unpacking stations, the utilization for a setup and buffer and all these things. So now you can understand where your time is being spent. What is interesting about this is if you start pulling on the levers and knobs, you find that you really don't need as many machines because you can optimize things. Optimize the plant layout so that your AGVs are traveling less. You can start changing the number of parts per year, the number of machines. It'll tell you how much availability. At the end of the day, this customer really only needed 30-some. This was huge. Coming into the project thinking they needed 60 machines, they only needed 30-some machines, was just amazing. What was even more amazing was to streamline the efforts. They were able to start manipulating the part design, so the digital twin of the product, and watching the impact on the shop floor all the way to the end. So think about when I show those circles and closing the loop and getting the OEE data back and feeding it back to the beginning. Now imagine taking your shop floor and optimizing the shop floor around the part design. That's another example of digitalization in your factory. Switch gears just a second here. Siemens, being who we are, we have facilities around the world where we can actually share our experiences with customers. What you see here in the picture is the headquarters for the AMEC, which is the Additive Manufacturing Experience Center in Erlangen, Germany. This is where my team sits. In this facility, we have robots, we have DMG Mori DED systems, powder bed fusion systems, multi-jet fusion systems. We have a lot of different machines. We have all of our software. We have all these digital twin tools set up so we can bring customers in and either give them the experience, show them how it works, or even run through a collaboration effort with them. This is huge because anytime we talk to someone about digitalization and that digital thread from end to end, it's like setting an elephant in the room. It's a giant undertaking that even some of the largest companies in the world we meet with look at us like, how do we do this? Well, we've built this system up so that you can eat that elephant one bite at a time. You don't have to take everything from PLM to industrial Internet of Things. You can take the pieces in between. That's why we've created these facilities. We have the HQ in Erlangen, Germany. We have an Additive Manufacturing Technology Center in Singapore. We have a demonstrator at MXD in Chicago we're working on. We have a demonstrator in our DEX facility in Campbell. And then most notably is our facility here in the U.S. that I'm responsible for. It's called CATCH. It's in Charlotte, North Carolina. It's the Charlotte Advanced Technology Collaboration. We're also planning a demonstration at LIFT in Detroit, Michigan. Because of COVID, we spent a lot of money building this experience center in Germany, and we were open about 9 months, had about 4,000 visitors come through there, and then COVID hit. And we thought, okay, we can't bring people through here. What do we do? Well, we're the experts in digitalization. So we created a virtual version of this, and we can schedule this for anybody who wants to see it. And I can take you on a virtual tour through this facility and run through use cases and software and machines, show you how it all works. And I'm absolutely pleased to say that we can do these things and show our entire portfolio, whether it be field device level, whether it be controller level, industrial edge, MindSphere, security, even some AI and some machine learning stuff we can show through here. And this is the interesting thing about Siemens is we cover this entire block, and we don't make machines. We don't make robots. We only make the solutions that will allow those things to work. Offerings are pretty simple. We can do virtual demonstrations of machines. We can do virtual hands-on with parts. We can do deep dives into NX, Team Center, Somatic IT, automation solutions, our factory simulations, all of these things, as well as our additive manufacturing network. To date, about 32 companies who were not using additive made the decision to start down the path because of their experiences at our Additive Manufacturing Experience Center. And then we actually help them through collaboration on that journey, help them plan that journey. What do they need? What kind of parts? How to train their people? So we bring these tools to the table. We don't just throw that elephant out there and walk away. 14 of these companies have reported back that without looking at AM as a complete digital process, they don't think their pilot programs would have been successful. And I would agree with them wholeheartedly. I've been in additive for a long time now, and I've seen it. I've seen companies try to bring additive in as a single piece and not look at it holistically, and it ends up being just making trinkets to go on desks, or it does a little bit of R&D work. But using it as a manufacturing tool, when someone takes this whole digitalization into account, they're much more likely to be successful. A little bit about our Charlotte Advanced Technology Collaboration Hub. We are located inside of Siemens Energy's turbine engine facility. Right picture there you see is looking from our mezzanine over one of the most impressive assembly bays. Most of those engines are about 24 to 30 feet in diameter. Our focus areas at Catch are obviously the Experience Center, so info tours, basic, but we're more focused on funded developments, whether it be internal Siemens business units or operating companies, or government institutional grants. We have a makerspace internal to Siemens, but most importantly is this collaboration hub. Today we have a dozen projects going on where we're collaborating with the printer OEM, whether it be for a hardware or software point of view, as well as our future of automation collaboration to advance additive. And we do a lot of end user collaboration projects as well as academic and industrial. When we say collaboration projects, it may be we go out and we apply for an SF grant or something like that to do something, or an end user comes to us and says, hey, who should we be working with? Can you assemble a team of OEM builders, academia, industry to get together to solve some pain points or some problem? And that's the focus of Catch and Charlotte. Basic collaboration could be just software, OEM, hardware to an end user, or deep dives could get into materials and processes, quality, as well as industry standards. Several of us sit on the F42 committee, so we have an insight into what's going on there. Here's a collaboration example where the customer wanted to see if they could use a hybrid situation to do mold repair. And what you see in the screen here is NX, manufacturing software, and you see a drone mold base, and it was damaged. So the idea was, can we import the part, topological optimization, prepare for the CAM functions, machining functions, and generate all the toolpaths? Well, fortunately, we used a DMG Mori hybrid system, which is all Siemens controlled. We have all the software tools built into NX for the system. And you can see on the screen here, we start going through the process. So we're going to mill away the damaged area. So you know exactly where it was. We picked it up with a probe, found it, mill away the damaged area, And then next, we're going to go on to doing a deposition. So we're going to build that area back up using DEDs, blown powder and laser. Then we'll go in and do a finish process to blend it all back in and do the final machining on it. Not every application in additive space works for hybrid situations. A lot of materials need post-thermal processing, but for a mold like this, it didn't require that. So what you saw, this is the virtual, so this is the VNCK of it, and here you can see the actual G-code processing and the deposition head, and now the finished machining. And on the right here, I'm going to start the second video showing the actual work. So here we're going to come in, we're going to mill away the damage. If you've ever been around one of the DMG systems, it's a very robust, very competent system. Now we're going to come in and we're going to rebuild this area where we just milled away all the damage. Keep in mind that the LaserTech system with DMG Mori is a very rough DED system. There are a lot on the market that are much finer resolution. But with a hybrid system, you don't need it to be refined very much. You just need to be able to throw the material down. So now you can see we're going to come in and do final machining of this rebuild area. And we've actually taken this to the next level. We have a project with call them a technology foundation, where we've taken a robot. We've used all these same tools, and we put a turbine blade in the cell with the robot. And the robot brings a probe out, picks up the blade, compares it to the solid model, determines where the damage is, machines away the damage, prints back up the built area on a turbine blade, machines it back down, and then does a final inspection. And it does it autonomously. And we've been able to leverage our advanced software and hardware capabilities to do this because we actually install CAM server inside of the control because our Cinemeric controls are that powerful. So the success and the deliverables from Catch are pretty simple. We want to enable the industrialization of additive with Siemens software and automation. Do this. We know we can only do this through collaboration. Can't be done alone. Siemens doesn't make machines. We don't do any of those things. We just help customers do their job better. I'm done a little early because I had 2 videos in there we couldn't show because we had audio problems.
All right. Thank you very much, Tim, for this wonderful presentation. Very fascinating, especially all the visuals you were able to show, and animation and videos. Okay. All right. So we got a couple of questions for you, Tim. I just wanted to thank you so much for taking the time to make this presentation. I know it was right after a vacation for you. So we're very happy that you were able to make this presentation. And it really fits well within our series because, Siemens is a large company working on additive. We had a previous speaker from Georgia Tech, assistant professor, working on additive, and he focused on machine learning for additive. And we're actually going to have another presentation next week from a small company, a startup, on additive as well. So we're getting a comprehensive picture of additive manufacturing here. So without further delay, I'll start with some of the questions here. So we have a question from Keith Dowsett. He says, to clarify, the primary role of Siemens is to provide manufacturers with PLCs for factory machine and the integrated simulation software. Is that correct?
Not necessarily. Our goal is to provide technology solutions, whether that be in software, everything from PLM to CAD, CAM to simulation. That's on the software side. On the hardware side, yes. Our role is to provide PLCs and integrated PCs and CNC controls to machine OEMs. Those are the 2 parts of our role in additive. And number 2 is Catch hiring electrical engineers. Not right now. But reach out to me on LinkedIn and we'll get your resume.
Yes, sir. We do have students watching. All right, we have
Absolutely.
another question from Michael Buzzy. He says, how detailed are the digital twins of the machines? Would you say this segment of the puzzle is solved, or is there a lot of work left to do?
Um, the detail of the digital twins is as deep as you want it to go. The software and the solutions have the capability to go all the way down to lubrication, right? So digital twin and lubrication on the slides or in the mechanisms of the machines. I don't want to say the puzzle's solved, but we're pretty far down the road. You know, we have a lot of software engineers who have worked on this solution for many years, and that whole digital twin of the machine started out in the automotive world, where they wanted to simulate their shop floors and their assembly processes as well as stamping processes. So we have over 30 years of experience of building these digital twins.
Awesome. Okay. Actually, we have another question, I believe, from a student who's wondering what background do individuals working in this field have? Are they advanced degrees, master's, PhD?
You know, I'm going to say, I'm going to give you the answer you don't want to hear. And the answer is it's more about passion. If you want to be involved in an emerging market, um, your degree is what the tool that you've learned with, right? You're coming out of school and you have a specific degree and a specific thing, and that's giving you the ability and understanding to do a specific job. But to get into the additive world, you have to be passionate about it because it's not an easy place to be. It's always immediately subjected to, well, what are the material properties? How do we know it's safe to use this? So it's an attacked industry more than traditional ones. Yes, it helps to have a master's in material science or a PhD in material science if that's where you want to go. But I've met a lot of people in this field with mechanical engineering degrees. I've met people with art degrees working in the additive space. So I wouldn't say there's a specific degree that's linked to it. Depends on what you want to do. There's many places to work at in this industry.
Excellent. We have another question from Keith. He says, when is Catch expected to finish construction? I see 13 months, but I'm not sure if that's an updated figure. And he also wants to know, are you based in Germany or the U.S.?
Catch, we are hoping to have a grand opening by mid to end of summer. COVID has made everything a moving target right now. So we're hoping that we get through the vaccine, people can start traveling again. We want to have the open house and we can have a lot of people come all over. I'm based in Cincinnati, Ohio, and we've just recently hired someone who's going to take care of Catch and scheduling all the things and driving all the work through there. Pleased to have him coming soon, and that announcement very
soon. I actually had a quick question myself, Tim, because you mentioned this this feedback loop that you have with your digital twins and optimizing the process. And I was wondering the role of machine learning or artificial intelligence in that feedback loop. I know machine learning is used in the generative design aspects, but we had a previous presentation on machine learning, so I just wanted to ask about that as far as Siemens processes.
Yes. So there's two answers to that. The first one on machine learning, yes. The control systems allow a level of machine learning. If I take, for an example, a DED process, the directed energy deposition. If you can have a digital twin coming in, right, you know what you want, you've simulated it, and you're going to actually build it. And while it's being built, if the control has the ability to collect sensor data, performance data from laser, powder feeders, the axis movement, it can start collecting all that data. It can build a digital twin output. Now, imagine that digital twin output is a bunch of numbers, but now we can convert it into geometry. So the machine learning is going to be putting out a digital twin at the end. And if we do this enough, then the machine can start doing some expectations. And I'm choosing my words very, very carefully because getting into digital twins and AI can be a very complex thing, and it's greatly misunderstood. I'm glad to hear that you had someone come on and talk about it, because we've been doing machine learning for many, many, many years. We have systems within our CNCs that can monitor the machine over time and tell you that bearings are going to go out in a spindle soon. Machines have this and been doing this for a very long time. Now, if you want to talk about making decisions in AI, we actually are the only company in the world that has a neural AI Intel chip embedded into our PLCs. So you can actually build up AI solutions in our systems very effectively. I'm not going to go into any details on AI projects because we'd be here for another hour, but we have focused for years on these tools and making these tools mainstream. One of the problems that I find is when you go into a manufacturer or an end user who says, we want to use AI, and you say, okay, where's your AI team? Because they think that their current team can just attack this, and it's not the case. You need people who understand AI, high-level math. You have to have the team together to start leveraging it.
Got it. And so, you, Tim, you are here in the U.S., right? But I guess you work quite often with Germany. You mentioned your supervisor was in Germany.
Correct. My boss is in Germany, and we call it Team Additive, and there's about 15 of us today. And our role is to make connections between end users, academia, industry, machine builders, and get all the right people together to industrialize additive. It's a very core group of subject matter experts. My expertise is in metal additive manufacturing as well as subtractive, and in the last several years have been around controls. So we all have our expertise, and the bulk of the team is in Germany. I was the first person in the U.S., and now we've hired a second person. But we work closely with all the application engineers and software engineers in all the different Siemens business units to make sure that we bring in expertise. We may have an AI expert in PLCs. He knows nothing about additive, but he knows exactly how to take and get the information in and back out that's needed.
Okay, right now I don't see any further questions. So I'm gonna just thank you again, Tim, for your time. Actually, we just have a question come in here. What are some future challenges you all are facing, such as market adoption, research, et cetera?
I think the future challenges are what we're all facing in the additive world, and that is material properties. In manufacturing, we like to look at material properties data, and we know that if we buy the 316 stainless bar stock, that its properties are fixed. But unfortunately, in the additive space, material properties are a end result of the machine's performance, right? So every job, that material could be a little bit different. Those are the challenges that we're facing. What we're doing at Siemens is we've already done it. We have digital simulations from a meso and a macro scale on material properties based on processes, whether it be laser power and cleanliness or powder size. And we're building those tools. And those are the biggest challenges: is first part right out of the machine and guaranteed quality. And that's what we're spending a lot of our time on today.
Excellent. All right. Yeah, we got just a couple minutes left, so I don't see any additional questions. So, Tim, I want to thank you one last time, for your presentation and your time. And I encourage anybody, if they have additional questions after this is over, you could reach out to Tim. His email address is tim.bell@siemens.com. And actually, we will make a recording of the lecture available upon permission of the speaker, and that will go on our website. A link to the recording will go on our website at research.gatech.edu/manufacturing/ lectures, past lectures. So I appreciate your time, Tim, and everyone's time. Next week, we'll actually have a startup company from Italy who will be talking about their journey actually to develop a startup company in additive manufacturing, focused on additive manufacturing. So that would be really interesting, particularly for students who want to learn about how to start a business. And they're actually interested in the U.S. market right now. So that would be from Mark One is the name of the company. So I encourage everyone to tune in next week as we continue our series. And with that, everyone have a great Monday. And we're going to
Thanks,
close.
Billy D.
You're welcome.